Hey there, ever watch something bounce up and down and just kind of wonder what makes it tick? That perfect repeating rhythm of a mass on a spring. Well, it isn't just simple. It's actually one of the most fundamental patterns in the entire universe. So today, we're going to unpack the physics of that simple yet really profound oscillation. Here's the game plan. First, we'll get down the basic rules of this motion. Then, we'll learn how to measure its rhythm, see how we can tweak it using mass and stiffness, understand the energy that actually drives it, and finally, discover where this incredible physics shows up all around us. All right, so what exactly is this motion? Anything that moves back and forth in a repeating pattern is oscillating, but we're going to focus on the cleanest, most predictable version of this movement, which, as you might guess, has its own special name. It's called simple harmonic motion, or just SHM for short. And that word simple is the real key here. It means the force that's pulling the mass back to its resting point is always directly proportional to how far you've moved it. This perfect, predictable relationship is all governed by a fundamental principle called Hooke's law. And this right here is Hooke's law. F is the restoring force, X is the distance you've stretched or compressed the spring, and K is just a number representing the spring's stiffness. But that little minus sign, that's the secret sauce. It tells us the force always pulls in the opposite direction of the displacement, constantly trying to get back to the center. That's the engine driving this whole thing. Okay, so we know what the motion is. Now let's talk about how we describe it. How do we measure the unique rhythm of this oscillation? We've basically got two main tools for this job. The period, that's the capital T, is simply the time it takes for one full cycle, back and forth. And the frequency, lowercase f, is the flip side. It's how many of those cycles happen in a single second. They're perfect inverses of each other. And here it is, the master formula. This one elegant equation tells you exactly how to calculate the period. It connects the timing of the oscillation directly to just two key things: the mass of the object and the stiffness of the spring. This is the recipe for the system's rhythm, and next we're going to start playing with the ingredients. So if that formula is our recipe, then the mass, m, and the spring constant, k, are our main ingredients. Just think of them as the two levers we can pull to completely change the motion of the system. And here's how those levers work. It's pretty intuitive. If you increase the mass, the whole system gets more sluggish, right? It takes longer to complete a cycle, so the period gets longer. But if you increase the spring's stiffness, make it harder to stretch, that spring is going to snap back much faster, causing a quicker oscillation in a shorter period. And this is a perfect way to think about it. We've all seen this. A diving board is just a type of spring. A heavier person has more inertia, so the board takes longer to move them up and down. Simple as that. More mass means a slower bounce. What's so cool is that our intuition here matches the math perfectly. Look at the formula again. Mass, m, is on top in the numerator. So a bigger mass means a bigger, longer period. Stiffness, k, is on the bottom in the denominator. So a bigger k gives you a smaller, shorter period. See? The physics just makes sense. Okay, so now we get the rules and the rhythm. But what's actually powering this endless back and forth motion? Well, the answer lies in this beautiful, continuous dance happening between two types of energy. Let's trace the energy through one full cycle. We'll start at the point of maximum stretch. At this exact moment, the mass has stopped moving, so its kinetic energy, that's the energy of motion, is zero. All of the system's energy is stored up in the spring as potential energy, just waiting to be unleashed. So as the spring pulls the mass back, all that stored potential energy gets converted into kinetic energy. Now, watch as it flies through the center, the equilibrium point. Right here, the spring isn't stretched or compressed at all. So for just an instant, all the energy is kinetic. This is where the mass is moving at its absolute fastest. Inertia carries the mass to the other side, and it starts compressing the spring. As it does that, the kinetic energy is converted right back into potential energy. When it reaches maximum compression, the mass stops again, its velocity is zero, and, you guessed it, the energy is once again 100% potential. The cycle is now ready to repeat. And this graph shows that whole energy dance perfectly over time. You can see the potential energy, U, and the kinetic energy, K, just perfectly trading places. They move in this beautiful inverse wave pattern. As one hits its peak, the other one bottoms out. But here is the most important part. The big takeaway: while those two forms of energy are constantly transforming into each other, look at that green line. Their sum, the total energy of the system, stays perfectly constant. This is a perfect example of the conservation of energy. No energy is being created or destroyed, it's just changing from potential to kinetic and back again. So we've gone through the theory, but this isn't just some concept in a textbook. The principles of simple harmonic motion are actually the foundation for countless technologies that we all use every single day. Seriously, just think about it. The shock absorbers in your car that smooth out a bumpy road, the tiny quartz crystal oscillating in your watch to keep perfect time, the strings on a guitar vibrating to create music. All of these things rely on the predictable, rhythmic principles of simple harmonic motion. And to wrap things up, here's a final thought question for you. Based on everything we've talked about, why does getting snapped by a ruler hurt way more than getting hit by a loose spring, even if you pull them both back the exact same distance? The answer lies in one of those key variables we explored today. I'll let you think.